As I said in class, we're now going to talk about radioactive decay and radioactive half-life. And I want to apologize for not being able to answer your question in class. I had forgotten that I had put this off to today, and I probably should have just put off the question until after you had the opportunity, and I had the opportunity to go over this information again. So anyway, radioactive half-life, as we've said over and over again, is the time required for half the atoms in a sample to decay. And this is just an example of cobalt, which has a radioactive half-life of about 5.27 years. And what you can see is if you start with a 10-gram sample, after one half-life, you have 5 grams. After 2 half-lives, you have 2.5 grams, and so forth. So after 5.27 years, you have 5 grams. After 10.54 years, you have 2.5 grams, etc. Now, the laws regarding radioactive decay go back to the chapter 12 that we discussed in the third quarter on kinetics, in which the decay constant, which was previously just called the reaction constant, is equal to the natural log of 2 over the half-life. This is a first-order kinetics problem, and that's equal to 0.693 divided by the half-life. Or the half-life is equal to the natural log of 2 divided by the decay constant. Now, the number of molecules remaining at any time t is equal to the number of molecules you start with times the natural times minus the decay constant t raised to the e power. And so if you rearrange that, t is equal to 1 over the decay constant times the natural log of the number of molecules you're looking at divided by the number of molecules you start out with. So as we've shown above, and I stated before, after 10.54 years you have 25%. After 15.81 years you have 12.5%. Now, you'll recognize this as coming from chapter 12, which we were looking at the same thing, and this is a graph which looks at the decay in terms of natural log divided by time versus time, and it is a mathematical expression of that, and this is a first order, and you'll see that this is very similar, that the natural log of the amount that you have at the end divided by the amount you started with is equal to minus kt. And so it's a linear relationship, and it's a first order reaction. And so the half-life of a first order reaction is calculated using the 0.693 divided by the decay constant. For a second order reaction, which is not relevant to our discussion here, you remember that it's equal to 1 over k times the initial concentration. And so this is the formula that you need in order to do the standard calculations. So let's take a look at a couple of problems in radioactive decay, and we might, if we get a chance, also take a look at the problem that we were doing in class. So here's the first problem. There's a polonium decays at with a half-life of 3.6 days. If one starts with a mole of atoms, 6.02 times 10 to the 23rd atoms, how many atoms are present after 20 days? So let's take a look at how we would do this. So first of all, we know that the half-life is equal to 3.60 days. And we know that we're starting out with 6.02 times 10 to the 23rd atoms, or nuclei. And the decay constant is equal to 0.693, which is the natural log of 2, divided by the half-life. So if we take 0.692 divided by 3.6 days, then the decay constant is 0.192 days to the minus 1. Now the number of molecules you have after any time t is equal to the number of molecules you start with times e raised to the decay constant times t. And so that's going to equal 6.023 times 10 to the 23rd times e raised to the minus 0.192 times, that's k times t, which in this case is 20 days. If you do the math here, you get nt is equal to 1.29 times 10 to the 22 atoms. The second problem says, how long will it take a 40-gram sample with a half-life of 8.04 days to decay to 1%? The natural log, this is just rearranging this equation here, the natural log of nt over n0 is equal to minus the decay constant times time. Now we have to calculate the decay constant. The decay constant, you'll remember, is equal to 0.693 divided by t1/2, or 0.693 divided by 8.04. So the decay constant in this case is equal to 0.0862 days to the minus 1. So that means that now the natural log of nt over n0 in 1% is going to be the natural log of 0.01 is going to equal to 0.0862 times t, and t is what we want to know. The natural log of 0.01 is 4.605, negative 4.605, and t is going to equal that divided by the decay constant. And so t is going to equal, and this is a minus sign here, excuse me, a minus sign there. So t is going to equal 53.5 days. Now let's take a look at some uses for these various calculations that we've just done. Now one of these is what's known as radioactive dating. Radiometric or radioactive dating is using isotopes to determine the age of things that are very old, archaeological artifacts. Carbon dating is using radioactive carbon-14 to provide the method for dating. And this diagram shows how this happens. Stable carbon-12 and radioactive carbon-14 are both taken in by plants and animals and remain at a constant level in them while they're alive. And that's because C14 has a very long half-life. After death, the C14 decays and the C14-12 ratio begins to decrease. Comparing this ratio to the C14-12 ratio in living organisms allows us to determine how long an organism has been dead. And this diagram shows that the decay only occurs in dead organisms. So this decay begins here and changes this ratio or decreases this ratio. So you compare the living to the dead ratio, and that tells you how long this decay has been going on. So carbon-14 dating can be used to date very old things, such as the Dead Sea Scrolls, which are pictured here, and the dating has been used to determine the age of this to be between 100 BC and 50 AD. Transmutation is the conversion of one nucleotide to another nucleotide. Transmutation reaction is the reaction that results in the change of one nuclei to another. This is a picture of a particle accelerator, and a particle accelerator is a device that uses fields, magnetic and electric fields, to increase the speed of nuclear particles, and these particles are then accelerated and banged into each other in order to cause a transmutation reaction. So this is just a small section of a nuclear accelerator or a linear accelerator, and a circle is generally used because it takes very long distances to achieve the acceleration you want, and if you're traveling in a circle, you can keep that in a confined area. So here's an example of a transmutation reaction. This is nuclear fission, or a division of U-235 to form two atoms, chromium or krypton 92 and barium 141, with the production of 3 neutrons. So fission is the breaking apart of a larger nucleus to form two or more smaller nuclei. A neutron strikes U-235. It is absorbed into U-235 to form the unstable U-236. This then breaks apart into barium 141 and krypton 92, and then 2 to 3 neutrons. And when this occurs, there's a release of a large amount of energy. Now this shows various fission reactions. The top one is the one fission reaction, and in each fission reaction you have a different set of nuclei that are formed. And which ones are formed are measured on the right here. So the nuclear fission can produce a range of various fission products. The larger fission products of U-235 are typically one isotope that's massed around 85, which is shown on the first peak on the right, and then another isotope which is about 50% larger, which is the second peak. And the first peak represents the krypton, and the second peak represents the barium. So these two peaks tell you that the bottom reaction of the 5 shown is the most common reaction that occurs. Now, a fission reaction can produce nuclei or neutrons as shown here, and those neutrons can go on to cause additional fission reactions in what's known as a chain reaction. So fissile material is a material that can sustain a fission chain reaction. So a material that is able to allow for this chain reaction to occur is called fissile material. So the fission of one large nuclei producing 2 to 3 neutrons, each of which can go on to cause the fission of another large nucleus, and this continues on in what's known as a chain reaction. Now, in order to achieve a chain reaction, a certain amount of material has to be present. The critical mass is the amount of fissionable material that has to be present in order to self-sustain a chain reaction. A subcritical mass is the amount of fissile material that is too small and allows too many neutrons to escape, such that the chain reaction does not continue. But critical mass is large enough number of neutrons and a large enough amount of fissile material to allow for a chain reaction to occur and to continue to occur. Nuclear fission is the earliest nuclear bomb, was secondary to nuclear fission. And this diagram shows how a nuclear bomb works. First, you start with A, where the nuclear fission bomb, which destroyed Hiroshima in 1945, it starts with subcritical masses of U-235. Conventional explosives are used to cram these two together in order to get a critical mass of material. Once critical mass is achieved, then this will then explode. The second bomb, which was a plutonium bomb, used a different mechanism in order to do this. And what basically happened is you have conventional explosives in a sphere around the outside of the plutonium. And these conventional explosives explode and force the plutonium closer to each other in order to reach critical mass. This bottom explosive device is easier to make and easier to use and uses material, plutonium, which is more available than the top nuclear device.